As shown below, a 0.2 kilogram mass is sliding on a horizontal frictionless air track with a speed of 3 meters per second when it instantaneously hits and sticks to a 1.3 kilogram mass, initially at rest on the track. The 1.3 kilogram mass is connected to one end of a massless spring, which has a spring constant of 100 newtons per meter. The other end of the spring is fixed. So part A asks us to determine the following for the 0.2 kilogram mass immediately before the impact: its linear momentum and its kinetic energy. Alright, so the equation for the momentum of an object is simply the mass times the velocity. And since this is a linear velocity, and these two are moving in a straight line, we don't have to do any of that stuff with like vectors and 2D momentum. So the momentum is simply going to be the mass times velocity of the mass that is sliding, which is simply 0.2 kilograms times 3 meters per second, which is 0.6 Newton seconds. Newton seconds is kilogram meters per second. And the kinetic energy is given by 1/2 mv squared. And that, we just have to plug everything in again. It's 1/2 times 0.2 times 3 squared. And that is equal to 0.9 joules of energy. So this is before the impact. So before the impact, momentum equals 0.6 Newton seconds, and kinetic energy equals 0.9 joules. So that's happens initially. Now B asks us to determine the following for the combined masses immediately after the impact: the linear momentum and the kinetic energy. So from momentum conservation, we know that the momentum before a collision is always equal to the momentum after the collision. And this is always true no matter what. So we can use this to help us out. So the mass of the small mass, the one that's initially moving, I'm going to call this little m, times the initial velocity, is equal to the combined masses, which is big M, the mass of the big block, plus little m. And this is because it sticks to the 1.3 kilogram mass, times the final velocity. So now all we need to do is solve for the final velocity, which is little m times the initial velocity divided by the combined mass. And now we just have to plug everything in. 0.2 times 3 divided by 1.3 plus 0.2. And now this should give you 0.4 meters per second. So the velocity after it collides is 0.4 meters per second. And we're going to use that to solve for the kinetic energy. And again, the momentum initially is equal to the momentum after. So the momentum after is still 0.6 Newton seconds. So nothing has changed there. Now we can use our new velocity to solve for the kinetic energy. Kinetic energy is 1/2 mv squared. M is now the combined masses, and v is the velocity after the impact. So now we just plug everything in again. This is 1.5 times 0.4 squared. This is equal to 0.12 joules. So the kinetic energy after the collision is 0.12 joules, which is a lot smaller than the initial one of 0.90 joules. So for part B, the momentum is still the same, 0.6 Newton seconds. The kinetic energy is now 0.12 joules, so smaller. So that's part B. After the collision, the two masses undergo simple harmonic motion about their position at impact, and C asks us to determine the amplitude of the harmonic motion. So now we have to use energy conservation. It's very similar to momentum conservation in that that energy cannot be created or destroyed, and it can only be transformed. And in this case, if there is no friction and nothing is lost to heat from the impact, and nothing is lost to heat as it moves the spring, the kinetic energy after the impact, I will subscript F to distinguish the two. The kinetic energy after the impact is equal to the energy of the spring, or the potential energy of the spring when it reaches its maximum point, or the amplitude. And the kinetic energy is 1/2 times the combined masses times the final velocity squared, which we found earlier to be 0.12 joules. So we can just plug that in for the final kinetic energy. KF. And the potential energy of a spring is given by 1/2 times the spring constant times the displacement square, where the displacement is how much that spring is compressed or stretched. So now we can just solve for x, as the displacement, the maximum displacement that it will reach, or the maximum spring potential energy it will reach, is equal to the amplitude. So we can just plug in a for amplitude for x squared. So from that we know that the final kinetic energy is equal to 1/2 k a squared, where a is the amplitude. Now we just need to solve for a. And so a is equal to the square root of 2 times the final kinetic energy divided by the spring constant k. So now we just have to plug everything in. I'm going to make a little more room up here. Now we just plug everything in. 2 times the final kinetic energy we calculated earlier of 0.12 joules, divided by the spring constant of 100 newtons per meter. And that is equal to 0.049 meters. So the amplitude is 0.049 meters. So that will be part C. Write it up here. C, the amplitude equals 0.049 meters. And now we need to determine the period of the harmonic motion. So the period is given by 2 pi times the square root of the mass divided by the spring constant k. So now we just need to plug everything that we know, which is 2 pi times the square root. The mass is actually the combined mass of the block that was initially moving and the block attached to the spring, since they stuck together and are now moving together. We're going to divide that by the spring constant. So just plug everything in. It's 2 pi to the square root of 1.5 divided by 100 newtons per meter. And so the period is equal to 0.77 seconds. Everything is in 2 significant figures. So for D, the period is equal to 0.77 seconds. And that is how you would solve this problem here.